Hello students, this is lecture number 7. We are done with chapter 2 and today we are going to learn something about computer implementation. Okay, so this is not any chapter in your textbook. Chapter 11 is about abacus and all. So basically you can take it at chapter 11. So uh, chapter 11 in your textbook talks about abacus, and abacus is a software, finite element software. However, here we will not I'm not going to teach anything about the abacus, but I assume I will send you some tutorial. If you go through them, then you should be able to run abacus. Here, rather than solving problem using abacus or ANSYS or anything, the idea is to have some capability to actually program and solve the problem. Okay, so long problems you cannot solve using just paper pencil. You will have to program, and as you can see, even like some problem, a small problem, something like this is a problem from your textbook only, chapter 2. This is problem 2.3 from your textbook. So here the so you have one bar here, another bar here, third bar here. Okay, this is nothing actually. uh, these are joints, and there is a force here, F equal to 10 Newton. E is given equal to 10 to power 11 Pascal, and area is also given. Area is equal to 2 times 10 to power minus 2 meter square. Coordinates are also given. So the first is uh, 0 0, this is B, 1 0, this is C, is 1 1, and this is D, which is 0 1. Yeah, all in meters. Now the question asks first number the elements and nodes. So we will see that this problem, okay, there is one more bar it has, like this one, otherwise it will not be a structure. So we have 5. Yeah, okay. So this problem we are going to program basically. Yeah, so first we will, let's do other parts of the question as well. So first it says number the elements and nodes. Okay, so let's use blue color for that. Number we will first do node numbering. So let's go say 1 here, 2 this one, 3 and 4. There are 4 nodes. So number of nodes equal to 3. Then we will do the element numbering. So let's start from here. So make it 1, this is 2, this is 3, and this is 4. So number of elements equal to 4. Okay. Okay. So, we are done. So, we have a numbered, that is the part A. Part B is assemble the global stiffness and force matrices. Okay. So, we have to find out the global matrix. Yeah. So, what we see here is we have different orientation. This one, for example, has theta equal to 90 degree, right. This one is 0, this is fine 0 degree, this is again 90 degree, this is actually if this is 1, this is 1, so this will be 45 degree from here to here 90 degrees, so 135 degree from the horizontal. So, accordingly we have to derive the stiffness matrix. Now, given that number of okay, I think I made a mistake. There will be number of nodes equal to 4. So, see here we have 1, 2, 3, 4. So, 4, but I wrote 3. So, it is not correct. So, let me correct it. So, number of nodes is also equal to 4. Okay. Okay. So, we will have to, in order to find out the stiffness matrix, we have to do all the rotation that we learned in the previous lecture video. Okay. Now, we have to first find out the global force matrix, global stiffness and force matrix. So, force matrix is easy to find out. So, we can also have the degree of freedom system as well. We can say here degree of freedom is this is the first one, call it, this is 2. Okay. Here we have number 3, this is number 4. At this point we have number 5 and number 6, and the top left we have number 7 and number 8. Okay. So, we have 8 degrees of freedom, hence size of K matrix means stiffness matrix will be simply 8 by 8. Okay. And the size of F vector will be equal to 8 by 1, and similarly the size of displacement vector will also be 8 by 1. Okay. Okay. Now, in order to solve these, of course, we if you see here which all degree of freedoms are fixed. So, we have 1, 2 fixed, 3, 4 fixed. What is not fixed is 5, 6, 7, 8. So, finally, we have to invert the matrix of 4 by 4. 4 by 4 matrix has to be inverted. Yeah. Okay. That may take some time if you do on the paper. So, we will take this example and try to solve using some program. Okay. Before that, let us write force vector, which will be easy. So, force vector we know here what is the force vector? We do not know, let us call it F1, F2. Here we know, we know displacement here. Okay. So, essential boundary conditions will be here U1 0, U2 0. Here it will be U3 0, U4 0, U5 we do not know, U6 we do not know, U7 we do not know, U8 we do not know. However, F1 F1 we don't know, F2 we don't know, F3 we don't know, F4 we don't know, F5 we know is equal to 10, which is given. F6 is 0 because no force given and it is not connected anywhere, means it is not connected to the outer some anything. Similarly, at this point no forces given, so F7 is 0, F8 is 0. So we can write displacement vector u is equal to, we have 0 0 0 0, then u5 u6 u7 u8. Okay, and f is equal to, where the displacements are constrained at points A, B or node 1 and 2, their forces we don't know. So we will write F1, F2, F3, F4. F5 is equal to 10 Newton is given, F6 is 0, F7 is 0, F8 is 0. So we have these forces. Okay, all are in Newton. Okay, now we have to find out K, and in order to find out K, we have to first find out what is the matrix of this one, this K matrix, what is the K matrix of this, which is easy to do. So if for 1 we can write K1 and we EA over L, we have to calculate for this one, and if this is a vertical, then we can use the rotation matrix to do it, or you can simply also you can do like this. For slant, we have calculated, we can use the equation for vertical one. For horizontal we know already what will be this one. For vertical it will be just rotation of 90 degree, and we don't need to actually multiply it by some rotation matrix, that's not needed. You know, we can just straight away write also. So let's see, for element number 2, let's start with that, that's easy. So element number 2, and what will be that? We have element number 2 like this. Okay, yeah, and the value E is constant, A is constant, L is equal to 1, right? So L equal to 1, and E and A we already have. So a small K matrix will be we have number 1 here, number 2 here, number 3 here, number 4 here. These are local, yeah, local numbering, and we will associate to the global one, we will do later. But here we can straight away we can write, if we had 2 degree of freedom system, total 2 degree means 1 degree of freedom per node system, we would have just EA over L, 1 minus 1 minus 1 1, yeah. And if you want to relate here, this for the 4 degree of freedom system, this will be 1, this will be 3, this will be 1 and 3, or yeah. So we have 1 here, we have 3 here, similarly this has 1 here, a 3 here. So basically in K new one, we are talking about K1, let's call it, this is a small K1, was 2 degree of freedom system. Big K1 is 4 degree of freedom system for the element. We can accordingly we can write, okay, how 1 2 3 4 1 2 3 4, and we will write K1 equal to, see here, this is 1 and 1, so this is 1 and 1, this will be, so we can first let's write Ka over L, sorry, Ea over L, just a minute, okay, so Ea over L, and 1 here, then we will have 0 minus 1 0 0 0 0 0 minus 1 0 1 0 0 0 0 0. This we also had yesterday, but still I am repeating, we have 1 and 3 and 1 and 3, hence we will write at 1 and 3 locations. So we have this 1 minus 1 minus 1 1. So this 1 will go here, this minus 1 will go here, this minus 1 will go here, this 1 will go here. That is what we are doing. Similarly, if this is for horizontal, if you had a vertical one, similarly you can do it, right. So we can write the same way, yeah. So we can here we have 1 like this, 2 like this, 3 here, 4 here, yeah. Maybe let's use different color, so we are not confused. So let's use blue color here. So 1 2, this is local numbering, 3 4, okay. So now if you look at it, we can still use the same one, but we have different degree of freedom now. So now this becomes 2, this becomes 4, right. So degree of freedom our changed. So in the new system we have written in blue color now, we have this 2 and 2 and 4 is along they are along this one, right. So basically what happens is 2, and instead of having 1 and 3 which were along the x axis now, earlier we have 2 and 4 which are along the x axis, hence instead of 1 we have in the new system we have 2, and here we have 4, here 2 and 4, hence 2 4 we have 2 4 like this one, right. So for this one, which is element number 1, so element number 1, we will have different k, and we will have K2 equal to Ea over L, and we can write, how will you write? We are going to one, 2, 3, 4, 1, 2, 3, 4, okay, and we have here 2 2, right, 2 2, we have 1, so we will write in 2 2 1, then we have 4 4 4 1, so we write 4 4 1, we have 2, and 4, 2, 4 minus 1. So 2, 4 minus 1 here. So minus 1, and similarly we have 4 minus 2, 4, 2 minus 1. So 4, 2 minus 1. So we have minus 1 here, rest all will be 0. Right. So this is how you can relate directly with the orientation. You just see the degree of freedom. You know that the 2 by 2 matrix system, we are only concerned with the degree of freedom which are along the x axis. So you know that in the global stiffness matrix 4 by 4 system, these only correspond to 4 and 2 only, and hence you can directly from here you can construct this one directly. No need to use the rotation matrix R. Okay. So element number 1 has been done, element number 2 has been done. Similarly, if you see 1 and 3 are same, yeah, both are vertical. So we, for this one we have done, this one we have done, and 3 is equal to 2 only, everything is same. So we can say that this is for element number 2 and also and 3. I can also write 3. Okay. Now number 4 is complicated meaning that we have to apply some rotation. Yeah. So for doing that, either we can also write directly the way we did earlier, cos square sin square theta, like that. That way also we can write, and here length is, you have to find out, we can write that way also, or you can. So this is for K4. So let me write here K2, just I will write here K. Okay. Just a correction, this is for element 2. So I will write here K2 here, and this is element number 1. So I will write number 1 here. Yeah, this is number 2, and K3 is equal to K1. Yeah. Okay. Okay. Now, so we have K1, K2, K3. Now K4 we have to find out. So directly also we can do. So K4, how to find out? Okay. So we have like this one, and angle here is theta equal to 90 degree plus 40 degree, 45 degree is equal to 135 degrees. Yeah, or this is equal to pi, is equal to pi over 2 plus pi over 4 is equal to 3 pi over 4 radians. Okay. So length is equal to, so here this is 1 0 1 coordinate, and here we have 1 0 coordinate. Okay. So basically this will be root 2 only, right. This let's write L4 equal to root 2, yeah, because it is 1 here, so this will be root 2. Okay, so we can directly write also how. First we have to write the stiffness. The stiffness will be simply EA over L4, right. So L4 is nothing but EA over root 2L, where L equal to 1, yeah. So we have used L equal to 1 earlier here, so same thing I am retaining here. So we have this. Now we can directly write K4 is equal to EA over root 2L, and then we can write here cos square theta, yeah. So cos square theta is, we can have cos theta is equal to cos 135 degree is equal to minus 1 over root 2, and similarly we have sin theta will be equal to 1 over root 2, yeah. So we know these values for this one, accordingly we can write it, okay. Okay, so we have cos square theta here, as we know. So cos theta is this, so it will be 1 over 2. So second is cos theta sin theta. So we have cos theta sin theta, so because minus 1 over 2 simply, right, minus 1 over 2. Rest we know this has to be negative of that, so we can write minus 1 over 2, and again this will be negative of this, so we have 1 over 2. Done. Now this is also symmetric, so whatever we wrote here we can write here, so repeat it, minus 1 over 2, minus 1 over 2, 1 over 2, done. Here it will be sine actually, so sine square theta, so sine square theta is 1 over 2, so 1 over 2. By the way, remember the diagonal values will always be positive, it has to be positive, yeah. So always make sure these values are positive, otherwise there is something wrong. So we have that. Now once we have that, we can have this as a negative of this and this as a negative of this. So we have 1 over 2 minus 1 over 2. We can again complete it, make it symmetric, so this will be repeated here. So 1 over 2 minus 1 over 2. Then we have here we have to fill in. So very easy, negative of this, negative of this, this negative of this, similarly this negative of this negative of this, and done. So we get 1 over 2 minus 1 over 2 minus 1 over 2 1 over 2. This is what you got. So we got all the things. We got K1 here, K2 done, K3 is equal to K1, and then we have K4 as well. E we know, A we know, L we know, all the values we know. Now next thing is just the assemble them, yeah. Okay. So how to assemble? So we can see the what is the global number, based on that we can do. So we have this, the global numbering system, we have 1 here, 2 here, 3 here, 4 here, 5, 6, 7, 8. So we have 8 by 8 matrix and we are going to assemble them. Okay, so let's do it. So big K, we are going to assemble all of them. So let's write K equal to, and make a big one. Yeah, and I will write also 1, 2, 3, 4, 5, 6, 7, 8. Okay, maybe I give more space. So write 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now similarly here also we will write 1, 2, 3, 4, 5, 6, 7 and 8. Okay. Now we should be able to fill this one. Okay. So we will make few things common. What? We will make EA over L common, and what we have, EA over L, and then we have root 2 as well. Root 2 here divided by 2. In other things we don't have like that. So even we can have 1 over 2 outside. So okay, or maybe we don't do anything. Okay, let it be like this only. We will have just E over L only outside common. Rest it, let it be like this one, so that you can also relate. So E over L I have written in common. So let's fill it up. Okay, so let's start with the this one, simple ones. So we have number 1, which is like this. Number 1 is vertical, and if it is a vertical member, vertical members we have like this, means the for the number 1 we have 3, 4, 5, 6, 3, 4, 5, 6. Okay, so accordingly, based on our derivation, we are going to write 3, 4, 5, 6, or you can directly also you can see that instead of copying from the 4 by 4 one, we can actually directly copy from there also. So instead of copying from here, you can also copy from just looking from here. What you will see is 4 and 6 are the one which are along this axis, hence E over L 1 minus 1 minus 1, one system will correspond to 4 and 6 only, right. So either we relate from here directly, or here we write the new system, and new system will be three, 4, new system will be 3, 4, 5, 6. This is what it is given, right. So we can write is 3, 4, 5, 6, 3, 4, 5, 6, and accordingly we can locate where these are, we can write. So this is 3, 4, 5, 6. So 4 and 6. So 4, 4, 4, 6, 6, 4, 6, 6. And same thing you can see here as well. 4, 6, 1 minus 1, 1 minus 1 minus 1, 1 system. So you got that. So we can write straight away in 4, 6 location. So this is a 4, this is the 6. Okay, so let me write this side also. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Okay, so 4 and 6. So 4 here, 4 and 6. Here we get 1 here. So let's write 1, 4, 4, 1, 4, 6 is minus 1, 6, 4, minus 1, 6, 6, 1, and we have common E over L already. So we have assembled element number 1 already. Okay, now element number 2, let's look at that. So element number 2 is here, and these corresponds to what? 5 and 7, right? So 5 and 7 are along this one. So E over L 1 minus 1 minus 1 1, that matrix will correspond to 5 and 7 only. So wherever we have 5 5 5 7 7 5 7 7, we can fill with 1 minus 1 and so on, or we can also relate it with here. So from here to here we have from 1 degree of freedom per node system we have this one, 2 degree of freedom per node we have, but we have local numbering. From here we have transferred that into global numbering. Global numbering, what we have? We have 7, 8, and then we have 5, 6. 7, 8, 5, 6. So this becomes 7, 8, 5, 6. 7, 8, 5, 6. Right? So what we get? We get 7, 7, 7, 5, 7, 5. That's what we are going to do. And we have to write at 7, 5, 7, 5 or 5, 7, 5, 7, the same thing because it's a symmetric. So I am going to write from the second element, we will have 7, 5, 7, 5, 7. Okay. So we have 5, 5 is 1, 5, 7 minus 1, 7, 5 minus 1, 7, 7, 1. Okay. Okay, so don't worry about the location. Actually the 8 we will write here. Okay, we will write here. Okay, so this is just for guidance. So this is actually 7 only. Okay. Okay, so we are done with element number 2, which is here. We have the common this one. This is for 2, this is for 1. Okay. Now number 3. Number 3, if you look at that, we have 1, 2, 7, 8. So we have 2 and 8 along this one. So at the location of 2, 8 means 2, 2, 2, 8, 8, 2, 8, 8, we can write 1 minus 1 minus 1, 1, right? Or we can have here 2 and 8 here. So, we have 1, 2, 7, 8. We can write here 1, 2, 7, 8, 1, 2, 7, 8, and then we can transfer this one, right. So, we can transfer the whole thing, we can write at 1, 2, 7, 8 location, 1, 2, 7, 8 location, right. Or simply we can have 2 and 8 will be at 1 and 0. So, this will be 2 and this will be 8, 2, 8, and we have 1, minus 1, minus 1, 1. So, at 2 and 8 we can write 1, minus 1, minus 1, 1. Okay, so let us have third, 2 and 8. So, 2 is here and 8 is here. Yeah. So, 2, 2 we will have 1, 2, 8 we will have minus 1, 2, 8 we will have minus 1, and 8, 8 we will have 1. Okay. So, we are done with the third one as well. Yeah, we are done with third one as well. Now remains the last one, node the element number 4, and for that we have 3, 4, 3, 4, 7, 8. We can we will not write here like we started from here, because our derivation earlier derivation it says which is fixed here, right, and then from here we are measuring some theta, right. So, all angle measurement will be with respect to horizontal like this. Okay. Okay. So, that means since we have taken this as our reference, from here we have done, hence the local number here is 1, this is 2, this is 3, this is 4, and this 1, 2, 3, 4 which is local correspond to global 3, 4, 7, 8, 3, 4, 7, 8. Hence, here this is the, we have 3, 7, 3, 4, 7, 8 system, 3, 4, 7, 8. Yeah. Hence, we have to write that. So, let me write this. This is 3, 4, 7, 8 global, 3, 4, 7, 8, and we can now copy. So, EA over L is common. So, we will have write 1 over 2 root 2 and so on. Yeah. 3, 4, 7, 8, half, minus half, minus half, half. Okay, that is what I am going to write. Of course, we will have root 2 as well. Okay. So, 3, 4, 7, 8. So, we have 3 here, 4, 7, 8, 3, 4, 7, 8. So, we start with 3, 3. So, which will be here 3, 3. Okay. So, 3, 3 we have to write 1 over 2 root 2. One over 2 root 2. Then 3, 4, 7, 8. Here we have minus 1 over 2 root 2. 3, 4 is done. Now 7. So, we will have minus 2 over root 2. Then we have 1 over 2 root 2. Done. First row is done. Okay. So 3, 4, 7, 8, second row, let's look at that. Minus half, 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 minus half. Yeah. So this is just opposite of this if you look at that, right. So minus of the above. So we will just copy on the in the fourth one. So in the fourth one we will have minus 1 over 2 root 2. Here already something exists, so we have to write here plus 1 over 2 root 2, right. We have to add it here. So we write plus 1 over 2 root 2, right, and then we will have 1 over 2 root 2 minus 1 over 2 root 2, done. Okay. Okay, now the next row we have similar to above only, exactly this row is exactly like this one only, but this is at 7, at the 7. So we write at 7, 7 is here, this is the 7 one, and then we have the 8 one. So 7 we have here minus 1 over 2 root 2, yeah. Then we have 1 over 2 root 2, okay. Then here already we have written here already we have 1, so we are going to add. So we will add plus 1 over 2 root 2, and then we have minus 1 over 2 root 2. Okay, done. Then last one, we have the opposite of the above, opposite of this, opposite meaning that the opposite sign. Okay. So number 8. So here we have 1 over 2 root 2 minus 1 over 2 root 2, and we have here minus 1 over 2 root 2, and we will have 1 plus 1 over 2 root 2. Yeah, because 1 is existing already, so hence we wrote like that. Okay. So now it's all complete. What we have seen is this black, the numbers in black coming from the element number 1, numbers in blue coming from element number 2, numbers in green coming from element number 3, numbers in red coming from element number 4, and we have the element, the matrix ready. We should have like let us see, at 1 we did not have anything in one direction here, k. So if you see here, in one direction there is no member here, right, and hence we will not see anything if you will not see anything in 1 1 at the 1 1 location. Yeah, so we do have in 2 2 but no 1 1, so that's why you get 0 in the first one. Anyway, so we are going to uh, write 0 at all the location where there is no numbers. Yeah. So what we get is 0, then 0, 0, 0, 0, 0. So we have, okay, there will be 0 here as well. So 1, 2, 3, 4, 5, 6, 7 and 8 done. Then again 0, 0, 0, 0, 0, okay, 0, then okay, just a minute, I think 1, 2, 3, 4, 5, 6, 7, 0 will be here also, sorry. So 0 here also, and here it will be 1, 2, 3, 4, 5, 6, 7 and 8. So 0 here as well. Okay, okay, done. Now we will have 1, 2, 3, 4, 5, 6, 7, 8. So there will be 0 here. Yeah. So let's write it. So we have 0, 0, 0, 0 here. Then we have 0, 0 here. 5, 6 will be 0. So 0, 0, and we will have a 0 here. Okay. Here also fourth one. So 1, 2, 3, 4. In 5 we will have 0. 5, 6, 7, 8. So we have 0 here. So 0. Okay. So 1, 2. So all empty here like this one, and 5. So 1, 2, 3, 4. So 1, 2, 3, 4, and then 1, 1, 2, 3, 4. So we have 0 here and 0 here. So 0 here and 0 here. Here also we have 1, 1, 2, 3, 4. So 0, 0, 0, and this is the fourth one. Then we have 1, 0 here, and then 0, 0. So 0, 0, 0. So we have 8. Similarly, the seventh one. So we have 1, 2, 3, 4, 5, 6, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So just 0 here. So we have 0 here. Similarly here 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. So 0, 0 here and 0 here. So we have 0 here and 0 and 0 here. So this is what the assembled stiffness matrix is. So here what we see is 8 by 8 system where we have 0, 0 coming in the first column and first row, because our degree of freedom 1 is there, but it is fixed here, so there is no bar in that direction. Okay. Now once we have that, we have to solve it. And how can we solve it? We have equation, and what equation we have? We will have k times u equal to f where k is like this one, what you see here, and u is as you have seen here. So, and f is like this one. So, we have 1 2 3 4 1 2 3 4 zeros. Hence, first 4 rows will be not used. So, only we have the last 4 rows and which will be used, and we have 10 0 0 in the fours. So, what we are going to use is last 4 which will be used. So, we have this one, this is what we are going to use, others will not be used. Okay. So, instead of writing the whole thing, I will write only the last 4 for 1. Okay. So, let us write it. Okay. So, we are going to write EA over L, and we have 1 0 minus 1 0, 1 0 minus 1 0, then we have 1 0 minus 1 0, 0 1 0 0, 0 1 0 0. Okay. Then we have minus 1 0, 1 plus 1 over 2 root 2 minus 1 over 2 root 2. So, minus 1 0. So, minus 1 0, 1 plus 1 over 2 root 2, then minus 1 over 2 root 2. Okay. And then we have 0 0 minus 1 over 2 root 2, 1 plus 1 over 2 root 2. So, we have 0 0 minus 1 over 2 root 2, 1 plus 1 over 2 root 2. Okay. So, this what we have multiplied by, we have x u 5 u 6 u 7 u 8 is equal to f 5 which is 10, then we have 0, then we have 0, then we have 0. Okay. And hence you can find out u1, the u5, u6, u7, u8 by inverting this one, right. So, this is and this matrix can be inverted, right. So, simply you can say now u5, u6, u7, u8 will be equal to L over EA, and then invert it 1 0 minus 1 0 0 1 0 0 minus 1 0 1 plus 1 over 2 root 2 minus 1 over 2 root 2 0 0 minus 1 over 2 root 2 1 plus 1 over 2 root 2, and invert it multiplied by 10 0 0 0 will be the answer. Once you have that, you can have all the displacement, but this is how you will solve on paper. Okay, so part C of the question was, part B was assemble the global stiffness and force matrices, that we have done. Part C is partition the system and solve for the nodal displacement. This is part C. This is part C. We have done nodal displacement. You can, but we have not inverted. Basically, I just wrote. Okay, so but this is a kind of big one. You can solve on paper, but it will take long time. And what we can do is we can use the computers to solve 4 by 4 the invert this one. So today I could not do programming, but tomorrow I will do the same problem. If I had to solve using computer programming, how will we do? Okay, so we have this ready so that you understand. Okay, so that's why the idea was to solve on paper first, and then we go to the computer and then solve the same thing. And number D, part D is compute the stresses and reactions. So once you get U3, U4, U6, U7, U8, you put them back in this the original matrix, this one. So you have U becomes 0 0 0 0, and then whatever you got this value, and you will multiply to K matrix, big K that we have assembled. This one will give you all the forces. Okay, so all the forces you will get, say all the values which is unknown. These are reactions F1, F2, F3, F4, where because at these degree of freedom are fixed, and hence you will get the reactions. So once you get the reactions, then only you will be able to find out the stresses, and stresses can be found out the way I explained in the last lecture video. Okay, so for today that is all. Yeah, so same problem we will solve using the computers. So we will do some programming in the next lecture video.